Good evening, everyone. This is Kalyan Kumar from Pi Mathematics Association. I take pleasure in welcoming you all to the third and final lecture on the second day of PMA Ramanujan lecture series. We sincerely apologize for the delay in starting this lecture session due to some technical difficulties. We apologize for the same. So we hope you all have really enjoyed the two sessions we had earlier today. So for the third session, we have our distinguished speaker, Index Supplement of the New Indian Express. And I'm happy to announce that our speaker has exactly answered the puzzles on multiple occasions and he has emerged as winner. So with this brief introduction, I request Ms. Sengodai Madam of Pi Mathematics Association to introduce our distinguished speaker to the audience. Thank you.
Vanakkam, good afternoon all. Now I am going to introduce Shri Rintoo Divakaran. He is a postgraduate in mathematics. He have done B.Ed degree and have a teaching experience of 1 year at a CBSE school in high school level. Along with his graduated, he did a 3 years diploma course in software engineering from Aptech, and he worked as a programmer in a software company for a short period of time. Presently, he is working as a senior grade assistant in Cochin University of Science and Technology. He has completed 10 years of services in CUSAT as on July 2020. He won prizes in various quiz competitions, both general and mathematics. He is regular solver of maths puzzles in edX New Indian Express newspaper since past 7 years and have been a winner of the competition for 24 times, continued till now. He have a desire to do research in mathematics, which he hope will succeed in future. Thank you. Welcome, sir.
Okay, shall I begin?
Yes, sir. Please, sir.
Yeah, shall I begin?
Yes, sir. You can begin, sir.
Okay. It's a matter of extreme pleasure for me to speak online. In fact, it is the first time in my life that I'm performing something online. And furthermore, when compared to the past 5 speakers, I'm nowhere behind. I'm not up to the mark of them as compared, because they are all eminent professors and I after all have only an year of school level teaching. But as mathematics is my favorite subject, and since I got this opportunity to speak about one of my favorite topics, that is number theory, I decided to go ahead with it. First, I shall just describe my relation with Pi Mathematics Association. As Kalyan sir said earlier, my relation with Pi Mathematics Association started with the answering of the puzzles. 7 years roughly back, that is in the year 2014, that is in the initial stages of 2014, I once just stamped upon the math puzzle which is published in edX every Monday, that is the educational supplement in the New Indian Express. As I told earlier, mathematics being a matter of interest for me, I started solving the puzzles regularly. Every week, I used to see that my answers were right. And after a couple of months, one day I saw that I was a winner in one of the week. Thereafter, I still continued again and again. And in between, I just searched for Pi Mathematics Association page in my Facebook. I found it, I liked it, and afterwards, at many of the times, the puzzles posted in the Facebook page, that too I answered, I received many appreciations. And around 4 years back, Shivaraman sir invited me to give a talk on some topic in mathematics. That is by coming to Chennai. At that time, we were free to travel. There was no situation of pandemic as we are facing now. But unfortunately, due to certain personal matters and some official busyness, I couldn't accept the offer at that time. Again, a couple of months back, Shivaraman sir called me and said that on this occasion, that is 133rd birthday of the great Indian mathematician Ramanujan, and further the 100th year, that is the centenary anniversary of the death of Shri Ramanujan, they are conducting a sequence of lecture series, and I invite you to give a talk on some topic which has relation with Ramanujan. Since I need not move from my place of residence, it is in the online means, I directly gave consent to his offer. And today I am in front to give lecture about one of my favorite topics, that is number theory. As far as this topic is concerned, that is the topic which I am going to lecture today. The role of Ramanujan is not much explained in it, but it is the general aspect. Now, before I get into the topic, that is before I get into the lecture, let me just speak a few words about Ramanujan. As far as Indians are concerned, I don't think that they have all realized the real essence of Ramanujan. Because if you check his history, it is very clear and evident. Born in 1887 in a poor Brahmin family at Erode, and with nothing to support, with no one to give a good pushback, he carried out all his research on his own. He developed deep theorems at a very small age, and whatever with the findings that he found were all noted in his famous Ramanujan's notebook. At England, it was Professor Godfrey H. Hardy who really mentored him and made him the real Ramanujan, that is, found the real mathematical genius in him. The Riemann zeta function, elliptic integrals, etc. are the two major ones for which Ramanujan has contributed. And at times, we all know, certain genius, their lifespan is quite short. Ramanujan also had the same. Due to depression and various personal pressures, at a time, he even tried to commit suicide. And finally, due to various health-related issues, at an age of 32, he died at Kumbakonam. Anyway, paying tribute to Ramanujan, I begin my lecture. Right. This is a page that you can see showing Ramanujan and his contributions. Next, sir. Yes. Now, getting to my topic, that is number theory, elementary concepts and theorems. When a child starts going to school and when he returns back home, the first thing that parents ask him is, what did you learn today? As far as the language is concerned, he will say, I learned ABC. And what about mathematics? Will he say that I learned calculus? Will he say I learned abstract algebra? Or I learned combinatorics or fuzzy mathematics? Or will he say I directly learned how to calculate the area of a square or volume of a cube? No. He will say, I learned 1, 2, 3. Now what? 1, 2, 3. What is this 1, 2, 3? They are numbers. And numbers are beautiful in various means. Now, as far as this lecture is concerned, we'll be mostly dealing with something that is very fascinating still continues to fascinate mathematicians both at professional as well as at amateur level, that is prime numbers. So prime number, that is the first thing that we are going to see. In general, what is a prime number? A number which has divisors only one and itself is called a prime number. The ready examples of prime numbers are the number 2, 3, 5, 7, 11, etc. Now, the first theorem that we are going to see in regards of prime number is that there are infinitely many prime numbers. That is, prime numbers are not restricted to 100 alone. Prime numbers are not restricted to 1000 alone. Prime numbers are not restricted to 10,000. Can I say that beyond 100 there are no prime numbers, or beyond 1000 there are no prime numbers? No, there are infinitely many prime numbers. Now let us see how to prove the same. For that, first we will assume that there are only a finite number of prime numbers, that is, say p1, p2, p3, etc., pn. Then let capital P, the variable capital P, be the product p1, p2, p3, etc., pn plus 1. That is, we are adding 1 to the finite number of prime numbers which we have assumed. That is, we have assumed initially that there are only finite number of prime numbers p1, p2, p3, etc., pn. We have multiplied them and added 1 to it, that product. Now, if p is prime, then it directly contradicts our assumption. What was our assumption? We assumed that there are only finite number of prime numbers, that is p1, p2, p3, etc., pn. Now what do we get? We are getting a new prime number which contradicts our assumption. And the proof is that there are infinitely many prime. So we take the other way around, that is, we are assuming that p is not prime. Then what can we say about capital P? Is it divisible by p1? Is it divisible by p2? Is it divisible by p3 or any of the previous primes? The answer is no. With any of the previous primes, when capital P is divided by any of the previous primes, that is p1, p2, p3, etc., pn, the remainder is 1. Now, a very important property regarding prime number is it is not divisible by any primes lesser than it. And quite similar to it, here we are getting a number that is capital P, which is not divisible by any of the previously assumed finite number of prime numbers. Then what type of a number is capital P? It results to be a prime number. Thus, in either ways, it contradicts our assumption that there are only finite number of primes. Hence, the number of prime numbers is infinite. That's it. Next. Yes. Now, we are going to see something interesting which we actually need to prove the next theorem. Right? Before that, we need this theorem. That is, it's not a theorem, it's a lemma actually. Euclid's lemma. Actually, lemma means applied logic. It is on the basis of logic that a lemma is stated. Now, let us see the statement of Euclid's lemma. Euclid's lemma states that if a prime P divides the product AB of two integers A and B, then P must divide at least one of those integers A and B. Right? So, let us see the proof of it. Yes. If possible, we will first assume that A is not divisible by P. So, we are having what in the initial stage, P is dividing the product AB. And it tells that either A or B or both must be divisible by P. For that, in order to prove this statement, we are assuming that if possible, let A be not divisible by P. Now, P is a prime number and A is not divisible by P. That means P and A are relatively prime. That is, their HCF or GCD, that is greatest common divisor, is 1. Then we have an identity called Besart's identity, which states that there are integers R and S such that RP plus SA is equal to 1. In fact, Besart's identity states that if A and B have GCD C, then there exists integers R and S such that AR plus BS is equal to C. Here, the greatest common divisor is 1. Thus, on the right hand side, we have 1, and the existence of R and S as stated, that is clear and evident. That is RP plus SA is equal to 1. Now, we are going to multiply both sides of this equation by B, and hence we get RPB plus SAB equal to B. Now, if you look at RPB, that is the first term on the left side. It is divisible by P because we have RPB. Obviously, it is divisible by P. Now, the second term, that is SAB. What is the specialty of SAB? SAB is divisible by the product AB. It is divisible. And what have we stated in the hypothesis part regarding AB? AB is divisible by P. That is, P divides AB, and we are interested in proving that P divides either A or B. So that is also clear that RPB and SAB are both divisible by P. Now, when two numbers are divisible by a third number, their sum also must be divisible by the same. Hence, their sum. What is the sum? RPB plus SAB equal to what? It is equal to B. And hence, since the left hand side is divisible by P, the right hand side is also divisible by P, and hence we get B to be divisible by P. So, if a prime number P divides the product AB, then P divides either A or B. The proof is quite similar if you assume the other way around also. That is, if you assume that B is not divisible by P and follow the same method by multiplying both sides by A, we get finally A is divisible by P. That's it. Yes. Now, the next theorem, which we are all interested in, it is called the fundamental theorem of arithmetic, or unique factorization theorem, or also unique prime factorization theorem. Let us get into the statement of it. It states that every integer greater than 1 either is a prime number or can be represented as the product of prime numbers, and this representation is unique except for the order of factors. That is, given any number above 1, it is either a prime number or it can be represented as product of primes except for the order of factors. I haven't written the example in it, but let us see. I'll just give you an example. That is, consider the number 12. 12, when we factorize, it is written as 2 into 2 into 3. This 2 into 2 into 3, instead we can write 2 into 3 into 2 or 3 into 2 into 2. The choice is ours. But in any case, the number 12 will have 2 2's and 1 3 in its prime factorization. Now, let us see how to prove the same. Now, first, we will show the existence of a prime factorization by the method of induction on n. Now, of course, in mathematical induction, we first show that a result is true for n is equal to 1 or a finite integer, and then we assume that the result is true for n is equal to k, and then we finally prove that the result is correct for n is equal to k plus 1, or the other way around. At times we assume that it is true for k n equal to k minus 1 and prove for k also. The choice. Anyway, finally proving all these three statements, we say that it is generally true for all n. That same way, here, first we will start with n equal to 2. As stated in the theorem, every number, positive integer greater than 1 is either a prime or a product of primes. Now, for n equal to 2, the statement holds, that is 2 is prime. Now, we are going to assume that it is true for all numbers greater than 2 and lesser than n. Now, if n is prime, then there is nothing to prove. Otherwise, we will have two numbers a and b such that n is equal to a into b, where a is greater than 1 and less than or equal to b and lesser than n. Then what do we have as per the induction hypothesis? A can be written as the product of primes. That is, we have written it as P1, P2, P3, etc., Pj, and B as the product of primes again, Q1, Q2, Q3, etc., Qk. Then what about the product A into B? It is nothing but P1, P2, P3, etc., Pj into Q1, Q2, Q3, etc., Qk. Thus, we have proved the statement to be true for all n. That is, there exists a prime factorization. Please rise, sir. Please rise. Rise the file. Yes. Next, we are going to prove the uniqueness. That is, we are going to show that this factorization is unique. For that, we are going to assume that n is the least integer which has two different prime factorization. That is, n equal to P1, P2, P3, etc., Pj, and also equal to Q1, Q2, Q3, etc., Qk, where each Pi's and Qi's are prime. That is, prime factorization, two distinct. We are going to show that such an existence is not possible. That's what we are going to do. Now, j and k are both at least 2. Of course, more than one factor, that is, we need 2 primes at least. Now, yes, we can see that we have P1, P2, P3, etc., Pj equal to Q1, Q2, Q3, etc., Qk. Now, on the left and on the right, we are having factors the same, corresponding to the same number. So, the product Q1, Q2, Q3, etc., Qk should be divisible by P1, which is also a factor, as per our assumption. Now, P1 dividing Q1, Q2, Q3, etc., Qk means by Euclid lemma, we have seen that it divides any one of the Qi's. Now, let us assume, without losing generality, that P1 is dividing Q1. Now, P1 and Q1 are both prime. So, one prime dividing the other, that means P1 is equal to Q1. So, we cancel P1 and Q1 on both sides. And what is the resultant? The resultant is P2, P3, etc., the product up to Pj equal to Q2, Q3, etc., up to Qk. Now, we have two distinct prime factorization of some integer strictly lesser than n. Why do we say that it is strictly lesser than n? Because P1 and Q1 has been cancelled. Had there been P1 and Q1 in the product, it would have been equal to n, which we have taken initially. Now we are having two distinct factorization for some number which is lesser than n. Now what does that mean? N is not the least number which has two distinct factorization, and that contradicts the minimality of n. Why did that contradiction occur? Because we assumed that a number has two distinct prime factorization. Thus, every number as per the unique factorization theorem greater than 1 has a prime factorization, and this prime factorization is unique except for the order of factors. That's what the proof says. Excuse me. Now, we are interested in finding the number of factors of an integer. Given an integer, it can be prime factorized, and it is so prime factorization that we are going to determine how many factors that the number has. So, if n is a given number, then we have n equal to p1 raised to n1, p2 raised to n2, etc., etc., pk raised to nk. Then the number of factors of n, it is equal to what? 1 is to be added to each of the exponent of the prime factors and the overall product. That is n1 plus 1 into n2 plus 1 into n3 plus 1, etc., nk plus 1. Now, let us see how we can prove it. We have the number n which has the prime factorization p1 raised to n1 into p2 raised to n2 into p3 raised to n3, etc., pk raised to nk. Then a factor of n will always have the form p1 raised to q1 into p2 raised to q2, p3 into p3 raised to q3, etc., pk raised to qk, where the value of q1 varies from 0 to n1, the value of q2 varies from 0 to n2 and so on. Now, I shall explain it in detail. That is, 1 is a factor of n. Obvious. How do we get this 1? For that, p1 should be raised to 0, p2 should be raised to 0, p3 should be raised to 0, and all the qk's should take the value 0. Thus, the significance of 0 here. Now, is p1 a factor of n? Yes, p1 is a factor of n. For that, how do we write the expression? p1 raised to 1 and the rest all, q2, q3, etc., qk, all are zeros. Now, the logic here is, thus, in the product of powers of pi's, there are n plus 1 possible powers of p1. That is, p1 can take how many powers? p1 raised to 0, p1 raised to 1, p1 raised to 2, etc., etc., p1 raised to n1. So how many powers can p1 have in this product? It can have n1 plus 1, that is including 0. We have to include 0 also. So there are n1 plus 1 possible powers of p1. Similarly, what about p2? It can also have 0, 1, 2, 3, etc. up to n2. So since we are including 0 also, p2 can take the powers. How many powers? n2 plus 1. And continuing this logic, that is this generalizing this pattern, pk can take powers from 0, 1, 2, 3, etc. up to nk. That is, since 0 is also included, it is nk plus 1. Now, we are having p1 raised to q1, sorry, p1 raised to n1, p2 raised to n2, etc. as the prime factorization. Now, using multiplication principle, that is, what is multiplication principle? It is a counting principle in which we state that if an event A can occur in n ways and another event B can occur in m ways, then they together can occur in m into n ways. Excuse me. Quite similar to it, here also the factors are obtained the same way. That is, p1 can occur in n1 plus 1 way, p2 can occur in n2 plus 1 ways. So the number of factors using multiplication principle, we get n1 plus 1 into n2 plus 1, etc., nk plus 1. Now, let us see some examples using this. First, the number of factors of 24. 24 is written as, that is the prime factorization of 24 is 2 cube into 3. Then using the formula that we have seen earlier, it is 3 plus 1 into 1 plus 1. What is this 3 plus 1? The power of 2 is 3. So it is 3 plus 1. And the power of 3 is 1. So it is 1 plus 1, that is 2. And we have 4 into 2, that is 8. Now, when the factors are listed, the factors are 1, 2, 3, 4, 6, 8, 12, and 24. So the 8 factors we have obtained and we have listed. Now, quite similar to it, a little slightly bigger number. The factors of 126. 126 is written as, that is the prime factorization of 126 is 2 into 3 square into 7. Then the number of factors of 126 using the same formula is 1 plus 1 into 2 plus 1 into 1 plus 1. Why 1 plus 1? The power of 2 is 1. So it is 1 plus 1. And the power of 3 is 2. So it is 2 plus 1. And the power of 7 is also 1. So it is 1 plus 1. And we have 2 into 3 into 2. That is 12. And the factors when listed are 1, 2, 3, 6, 7, 9, 14, 18, 21, 42, 63, and 126. So the 12 factors we have neatly listed. See the beauty of the formula and mathematical logic applied. Right. The next one is sum of the factors of an integer. Again, as in the previous theorem, that is in the previous formula, we have n having a prime factorization p1 raised to n1, p2 raised to n2, P3 raised to N3, etc. Pk raised to Nk. Then the formula for the sum of the factors of n is given by P1 raised to N1 plus 1 minus 1 upon P1 minus 1 into P2 raised to N2 plus 1 minus 1 upon P2 minus 1, etc. etc. And the final product is, that is Pk raised to Nk plus 1 minus 1 the whole by Pk minus 1. Now let us see the proof for it. For that, we have to consider the expression, that is the first term is 1 plus P1 plus P1 square plus etc. etc. plus P1 raised to N1, and that is multiplied to 1 plus P2 plus P2 square plus etc. etc. plus P2 raised to N2, and finally the term is 1 plus Pk square plus etc. etc. plus Pk raised to Nk. Now, when you multiply this completely, we can observe that it contains each of the factors. That is, it will have how many terms? The formula for the prime for the number of factors that we used earlier, it is n1 plus 1 into n2 plus 1, etc. That many number of terms this particular expression, when expanded, will be having, and each of the term in that resultant will be a factor of n. And yes, as shown in this, the sum of all the factors of n, as each term is in the final product, is a possible value of P1 raised to Q1. Yes, as stated in the previous formula, we have 1. 1 will be the constant term that is available here in this expression. How do we get 1? It is P1 raised to 0 into P2 raised to 0, etc. Pk raised to 0. Yes, so the variation of Qi's are from 0 to ni's. That's what for I equal to 1, 2, 3, etc. k. Now 1 plus P1 square plus etc. P1 raised to N1. It is nothing but the sum to N1 plus 1 terms of a geometrical progression whose first term is 1 and the common difference is P1. Here P1, it is greater than 1, so we have the formula for it as P1 raised to N1 plus 1 minus 1 by P1 minus 1. Now, applying the same formula for the remaining ones also, we get P2 raised to N2 plus 1 minus 1 by P2 minus 1, P3 raised to N3 plus 1 minus 1 by P3 minus 1, etc. And so the sum of the factors of n, that is the product which we get, is finally P1 raised to N1 plus 1 minus 1 by P1 minus 1 into P2 raised to N2 plus 1 minus 1 by P2 minus 1, etc. etc. Pk raised to Nk plus 1 minus 1 by Pk minus 1. Thus, the sum of the factors of an integer having prime factorization P1 raised to N1 into P2 raised to N2, etc. etc. Pk raised to Nk is shown. Yes, now we have a couple of examples for that. Find the sum of the factors of 24. 24 is equal to 2 cube into 3. Then the sum of the factors of 24 is equal to what? 2 raised to 3 plus 1 minus 1 by 2 minus 1 into 3 raised to 1 plus 1 minus 1 by 3 minus 1. The formula we are applying, 2 raised to 3 plus 1, that is n1 plus 1 formula we are using here. So 2 raised to 4 and 4 minus 1, and the second one is 3 raised to 2 minus 1, and on the bottom we have 2 minus 1 into 3 minus 1, and finally we get 15 into 4 equal to 60. Now, if you list the factors of 24, they are 1, 2, 3, 4, 6, 8, 12, and 24. When you sum up these 8 factors, we get 60 as the applied by the formula. Now, the sum of the factors of 100. 100 has the prime factorization 2 square into 5 square. Then, using the previous formula, what we get? The sum of the factors of 100 is equal to 2 raised to 2 plus 1 minus 1 by 2 minus 1 into 5 raised to 2 plus 1 minus 1 by 5 minus 1. Why 2 plus 1? Because we have in the formula P1 raised to N1 plus 1 minus 1 by P1 minus 1 into P2 raised to N2 plus 1 or minus 1 by P2 minus 1, etc. Now that on simplification, we get 2 cube minus 1 by 1 into 5 cube minus 1 by 4, which is equal to 7 into 31, 217. Now, when we list the factors of 100, that is 1, 2, 4, 5, 10, 20, 25, 50, and 100, and sum them up, we get the outcome. That is a sum as 217. So again, the beauty of mathematics is very well seen. Instead of finding out all the factors and adding them up, if one knows the prime factorization of the given number, that is 100, it is very easy to compute the sum of the factors. Yes, that's it. Yes. As we go ahead and ahead, more interesting topics are coming. Next is Euler's torsion function or Euler's phi function. Now, let us see what is Euler's phi function. Before going to Euler's phi function, I would like to give you a small concept, that is the concept of relatively prime. What does relatively prime mean? Two numbers are said to be relatively prime if their GCD is 1. Now, we are interested in counting the number of numbers that are lesser than a given integer n and prime to n. For example, I'll just give the number 6. If you consider the number 6, it has two numbers which are lesser than 6 and prime to 6, that is the number 1 and the number 5. The remaining ones have GCD greater than 1, that is the number 2 and 6 have GCD 2, the number 3 and 6 has GCD 3, and the number 4 and 6 of course has GCD 2. Now, we are having a formula for finding the number of numbers lesser than n and prime to n. Please expand the slide, sir. Slide. Please expand to 100%. I think there is some technical problem. Please expand the page to 100%, sir. Sir, the previous page, sir. Please expand it to yes. Thank you, sir. Thank you. Right. Now, yes, Euler's phi function. So as I told, we are interested in seeing the number of numbers lesser than n and prime to n of the given integer n. Now, if n has a prime factorization p1 raised to n1 into p2 raised to n2 into etc. pk raised to nk, then as per Euler's phi function, phi of n is equal to n into 1 minus 1 by p1 into 1 minus 1 by p2 etc. 1 minus 1 by pk. Now, in order to prove this formula, we are going to prove two things. That is, first, if m and n are relatively prime, then phi of mn, that is the product m into n, is equal to phi of m into phi of n. For that, we are going to take three sets A, B, and C of positive integers that contain all the numbers lesser than and prime to m, n, and mn respectively. That is, the set A contains all those integers which are lesser than m and prime to m. The set B contains all the integers that are lesser than n and prime to n. And the set C contains all those integers which are lesser than the product mn and prime to mn. Right. Now, we have an important result. That is an important result using the Chinese remainder theorem. That is, there is a bijection between A cross B and C. A cross B is nothing but the Cartesian product of A and B and the set C. Now, what is a bijection? A bijection is said to exist when every element that is in two sets, say x and y, there exists a bijection if every element in X has an image in Y. And every element in Y has a pre-image in X. In general, we say that it is 1-to-1 and on-to. That is, every element in one set has a unique image in the other set. And every element in the other set has a unique pre-image in the previous set. Quite similar to it here, as per the Chinese remainder theorem, there exists a bijection between A cross B and C. And when there exists a bijection between two sets, then that two discrete sets, their cardinalities are the same. That is, the cardinality of A cross B is the same as, is equal to the cardinality of C. And the cardinality of the Cartesian product A cross B is cardinality of A into cardinality of B, and that is in turn equal to cardinality of C. Now, what does A contain? A contains the set of, A is nothing but the set of all prime numbers which are lesser than n, and so lesser than m and prime to m. So cardinality of A is nothing but phi of m. And what about cardinality of B? What does B contain? B contains all those integers which are lesser than n and prime to n. So cardinality of B is nothing but phi of n. And similarly, what does C contain? C is the set of all integers lesser than mn and prime to mn, and hence cardinality of C is phi of mn. So we have proved that if m and n are relatively prime, then phi of mn, that is phi of the product mn, is equal to phi of m into phi of n. Now we prove that phi of p raised to k is equal to p raised to k minus p raised to k minus 1, or in other words, that's the final term I shall say, p raised to k into 1 minus 1 by p. Here p is a prime number and it has an exponential representation of p raised to k. For example, the numbers like 2 raised to 6, 2 raised to 8, 3 raised to 5, etc. For such occasions, this formula has to be applied. Now, yes, let us see how we can prove it. Yes. Given an integer m along other than p raised to k, since p is prime, the only possible values of the HCF of p raised to k and m are the exponential values of p, that is 1, p, p square, etc., etc., p raised to k. And HCF of p raised to k and m will be greater than 1 if and only if m is a multiple of p. That is, if we have m equal to p, 2p, 3p, etc., up to p raised to k minus 1 into p, that is p raised to k minus 1 into p is nothing but p raised to k. Yes, for those values alone, that is those integral multiples of p alone, the HCF of p raised to k and m are greater than 1. Hence, the rest, yes, 1, 2, 3, etc., we had how many integral multiples of p? P raised to k minus 1 integral multiples. So, how many numbers are remaining with GCD equal to 1? It is p raised to k, that is the difference between the numbers. P raised to k minus p raised to k minus 1 numbers are all relatively prime to p raised to k, and hence phi of p raised to k is equal to p raised to k minus p raised to k minus 1, and that is as stated, p raised to k into 1 minus 1 by p, the final result. Okay, now we are going to prove the original formula. That is, we have an integer given, its prime factorization, that is n is given to be n1 raised to sorry, p1 raised to n1, p2 raised to n2, etc., pk raised to nk. And now in order to prove that phi of n is equal to this, that is n into 1 minus 1 by p1 into 1 minus 1 by p2, etc., 1 minus 1 by p suffix k. Yes, we are going to take phi on both sides, that is phi of n equal to phi of p1 raised to n1 into p2 raised to n2, etc., pk raised to nk. Now, each of the pi's, that is p1, p2, p3, etc., pk, are all prime, right? Prime in the sense they are relatively prime to each other. Hence, their exponential part is also relatively prime to each other. That is, p1 raised to n1, P2 raised to N2, etc., Pk raised to Nk, all are relatively prime to each other. So we saw a theorem earlier. That is, if m and n are relatively prime, then phi of m into n is equal to what? Phi of m into phi of n. That we are applying here. That is phi of p1 raised to n1. That is, we get phi of p1 raised to n1 into phi of p2 raised to n2, etc. Phi of pk raised to nk. Now, the second theorem again comes to the role. That is, we proved that for a prime power, that is, if p1 is raised to k1, we have p1 is raised to k, we have a formula, that is p raised to k minus p raised to k minus 1, and finally it is equal to what? P raised to k into 1 minus 1 by pk. Quite similar to it, we have phi of p1 raised to n1 is equal to what? P1 raised to n1 into 1 minus 1 by p1 into p2 raised to n2 into 1 minus 1 by p2, because each p1, p2, p3, etc., pk are all primes, and their exponentiation is n1, n2, etc. And so that's it. So p1 raised to n1 into 1 minus p1 into p2 raised to n2 into 1 minus p2, etc., pk raised to nk into 1 minus pk. Now we are grouping the terms. That is the right hand side, we are grouping the terms, and we get p1 raised to n1 into p2 raised to n2 into etc., pk raised to nk into 1 minus 1 by p1 into 1 minus 1 by p2, etc., 1 minus 1 by pk. Now what is p1 raised to n1 into p2 raised to n2, etc., pk raised to nk? It is a prime factorization of n. So that is being substituted by n, and so phi of n is equal to n into 1 minus 1 by p1 into 1 minus 1 by p2 into 1 minus 1 by p3, etc., 1 minus 1 by pk. Hence, the formula for Euler's Cochin function is described. Now, yes, we are having a couple of examples. Find the number of numbers lesser than and prime to 24. Now, 24 is equal to 2 cube into 3. Then by Euler's phi function, phi of 24 is equal to 24 into 1 minus 1 by 2 into 1 minus 1 by 3. That is, we saw the formula earlier. Phi of n is equal to n into 1 minus 1 by p1 into 1 minus 1 by p2, etc., 1 minus 1 by pk. Here the prime factors we have for 24 are 2 and 3. So phi of 24 is equal to 24 into 1 minus 1 by 2 into 1 minus 1 by 3. And that on simplification we get 8. Now if you list the 8 numbers which are lesser than 24 and relatively prime to 24, we can see that it is 1, 5, 7, 11, 13, 17, 19, and 23. Can we take 21? Can we take any other number, say 15? No, because 21, 15, etc. has GCD equal to 3 with 24. So the beauty again has arrived. Now, yes, another example. Find the number of numbers lesser than and prime to 30. 30 when prime factorized, it is 2 into 3 into 5. So phi of 30 is equal to 30 into 1 minus 1 by 2 into 1 minus 1 by 3 into 1 minus 1 by 5. That is on simplifying, we get 30 into half into 2 by 3 into 4 by 5, which is again 4 into 2, 8. Now, if you list the numbers which are lesser than 30 and prime to 30, we get 1, 7, 11, 13, 17, 19, 23, and 29. So these are the numbers which are lesser than 30 and relatively prime to 30. Next, we are going to deal with another concept, that is convergence. Actually, convergence comes as a concept in a part of arithmetic, that is in a field of arithmetic called modular arithmetic. Yes, why modular arithmetic? In the sense, we will be using the terminology modulo. Now, let us see what it is. Given 3 integers a, b, and c, we say a is congruent to b mod c, that is b modulo c, if a minus b is a multiple of c. Yes, here c is not equal to 0. Now, congruence modulo n is an equivalence relation. What is equivalence relation? A relation which proves to be reflexive, symmetric, and transitive is called a equivalence relation. Now let us see how convergence modulo n is an equivalence relation. A is congruent to A modulo n. Is it not? Yes. Because A is congruent to A modulo n means A minus A is a multiple of n. What is A minus A? A minus A is nothing but 0 and it is a multiple of n. Right. Now the next one is symmetric relation. If we say A is congruent to B modulo n, then B is congruent to A modulo n. How? Let us see how it is. A is congruent to B modulo n means A minus B is a multiple of n. Then how can I write B minus A? I have to take minus and say B minus A. If 10 is a multiple of 5, of course minus 10 is also a multiple of 5. Quite in a similar way, we get B minus A also to be a multiple of n, and that in turn means B is congruent to A modulo n. Now the third one is the transitive relation, that is the spreading relation. If A is congruent to B modulo n and B is congruent to C modulo n, then A is congruent to C modulo n. Yes. Now examples for that we can see here. 3 is congruent to 1 modulo 2. Yes. 3 minus 1, 2. It's a multiple of 2. Yes, 2 is a multiple of 2. 7 is congruent to 2 modulo 5. How? 7 minus 2, that is 5, is a multiple of 5. Similarly, 27 is congruent to 3 modulo 4. How? 27 minus 3, it is 24. It's a multiple of 4, of course. And another one, by taking a minus number on the right hand side, 27 is congruent to minus 1 modulo 4. Yes, 27 congruent to minus 1 modulo 4. When minus 1 is brought to the left hand side, it becomes plus 1 and we get 27 plus 1, that is 28. It's a multiple of 4, of course. So that part also is clear. Now, certain properties and laws of cancellation in convergence modulo. Let us see how it is. First one, if A1 is congruent to B1 modulo n and A2 is congruent to B2 modulo n, or if A is congruent to B modulo n, then we have the following properties. First, we have stated A1 is congruent to B1 modulo n, A2 is congruent to B2 modulo n. So the sum, that is A1 plus A2, is congruent to B1 plus B2 modulo n. Then that is, it is compatibility with addition. The next one is A1 minus A2 is congruent to B1 minus B2 modulo n. Compatibility with subtraction. The next one is A1 A2 is congruent to B1 B2 modulo n. What is it? Compatibility with multiplication. Now, next one, that is with, we are seeing that with, if A is congruent to B modulo n, that part we are seeing. If a constant k is added to both sides, then A plus k is congruent to B plus k modulo n. Scalar multiplication, that is, of course, integer, we are multiplying. Ka is congruent to kb modulo n. And final one is exponentiation, that is, A raised to k is congruent to B raised to k modulo n, and this is valid for k being a positive integer. Next, we have 3 laws of cancellation. That is, if A plus k is congruent to B plus k modulo n, or if Ka is congruent to Kb modulo n, or if Ka is congruent to Kb modulo k, in all these cases, it means that A is congruent to B modulo n. How do we get it? In the first one, that is A plus k is congruent to B plus k mod n, we cancel k on both sides. The constant k which we have added on both sides are cancelled. Then in Ka is congruent to Kb modulo n, we cancel the the constant which we have multiplied on both sides, that is k, and we get A is congruent to B modulo n. And Ka congruent to Kb modulo kn, k is taken overall outside and cancelled, and we get A is congruent to B modulo n. That's it. Yes. Now we are having some interesting theorems based on modulus operation. The first one is Fermat's little theorem. Before going to the theorem, Pierre de Fermat, a great French mathematician who lived in the period 1601 to 1665. One theorem which had fascinated mathematicians for about 3.5 decades Of course, that is not Fermat's little theorem. It was Fermat's last theorem. That theorem, of course, it stated that x raised to n plus y raised to n equal to z raised to n has no integral solutions for x, y, and z when n is greater than or equal to 3. And of course, we all know it was Andrew Wiles who proved the theorem in the year 1995. Many mathematicians previously had tried, and of course, in their lifespan, they couldn't achieve. And the line that Fermat had said, of course, it's a great word. I have a proof, but it is beyond the scope of this book. That is, this book cannot accommodate the proof. Right. Now, about Fermat again. Fermat, along with Blaise Pascal, had laid down the foundations of probability theory, which is very well used in statistics. Now, we are having Fermat's little theorem. Let us see what Fermat's little theorem states. If P is a prime number and does not divide A, then A raised to P minus 1 is congruent to 1 modulo P. Or in other words, A raised to P minus 1 is a multiple of P. Yes. For that, we are going to take some cases. That is, let A be congruent to R1 modulo P. Let 2A be congruent to R2 modulo P. 3A be congruent to R3 modulo P, etc. etc. P minus 1 into A is congruent to R P minus 1 modulo P. Since P is prime and does not divide A, P does not divide any of the product, that is A, 2A, 3A, or P minus 1 A. Thus, Ri's cannot be equal to 0 for any I. And further, we have R1, R2, R3, etc. Rp minus 1. What are they? They are nothing but the remainders obtained when divided by P. That is, any number when divided by another, we get remainders which are lesser than it. So it is here 1, 2, 3, etc. up to P minus 1. And we have seen earlier that it cannot be equal to 0. And now we are going to further show that all the Ri's are distinct. How? For that, we take a case. Ra is congruent to C modulo P, and another one, that is Sa, is also congruent to C modulo P. Then, using the transitive relation form, we get Ra is congruent to Sa modulo P, which means R is congruent to S modulo P. How? We have cancelled A on both sides. That means R minus S is a multiple of P, which is impossible because R, S, etc. are all lesser than P and relatively prime to P. So R minus S can never be a multiple of P. Now we are going to multiply on both sides and take the modulo operation. That is A into 2A into etc. etc. That is, we are multiplying all the values. We initially took A is congruent to R1 modulo P. 2A is congruent to R2 modulo P, etc. etc. So on the left hand side, we have A into 2A into 3A, etc. etc. up to P minus 1 into A. And on the right hand side, as stated earlier, what are Ri's? R1, R2, R3, etc. are nothing but 1, 2, 3, etc. up to P minus 1 in some order. So it is 1 into 2 into 3, etc. P minus 1 modulo P. Now, when the product is taken, it is A raised to P minus 1, and we are multiplying 1 into 2, that is A is multiplied P minus 1 times, so it is A raised to P minus 1, and 1 into 2 into 3, etc. we are multiplying up to P minus 1, so it is P minus 1 factorial. And on the right hand side, of course, it is 1 into 2 into 3, etc. up to P minus 1, that is P minus 1 factorial we are having. So, as earlier, A raised to P minus 1 into P minus 1 factorial is congruent to P minus 1 factorial modulo P. What can we do? An easy step, we have to cancel P minus 1 factorial on both sides, and we finally get A raised to P minus 1 is congruent to 1 modulo P. That is a raised to p minus 1, the whole minus 1 is a multiple of p when p is prime and when it doesn't divide. Okay. That's it. Yes, next. Sir, the next page, sir. Yes. Next, another interesting theorem, Wilson's theorem. The thing here is, it was stated by John Wilson, and the proof of it was given by Lagrange. Lagrange was a great mathematician, a French mathematician, and it was given in the year 1771. Now let us see what Wilson's theorem states. Wilson's theorem states that given an integer p greater than 1, p minus 1 factorial plus 1 is divisible by p. That is, it's a multiple of p. P minus 1 the whole factorial plus 1 is a multiple of p if and only if p is prime. That we can very well see. For example, take the number 2. 2 minus 1, that is 1. 1 factorial plus 1 is 2. It is divisible by 2. 3. 3 minus 1, that is 2. 2 factorial plus 1. It is equal to 3. It is divisible by 3. 5. 5 minus 1, it is 4. 4 factorial is 24. 24 plus 1, it is 25. It is divisible by 5. And it goes on. Now, let us see how we can prove it. Yes. First, we have to prove both sides. So first, p minus 1, the whole factorial plus 1 is divisible by p, and we are going to prove that p is prime. If possible, let p be not prime. That is, let p be a composite number. Then, of course, if it is composite, it will have a divisor which is greater than 1 and lesser than or equal to p minus 1. Lesser than p, that should be taken to account. And then, what? If the number d is it's one of the factors, then it of course divides the factorial, that is 1 into 2 into 3 etc. up to p minus 1, that is p minus 1 factorial, because d will also be included in that factorial. So it divides, that is d divides p minus 1 factorial. Now since it divides p minus 1 factorial, it cannot divide 1 added to it. It cannot divide p minus 1 the whole factorial plus 1. Thus our assumption that p is composite is wrong, because we were initially given that p minus 1 the whole factorial plus 1 is divisible by p. But where did we arrive at? We arrived at a situation that p minus 1 the whole factorial plus 1 is now not divisible by p. Why did such a contradiction occur? It occurred because we assumed that p is not prime, and that is p is composite. Hence the correct part is p is prime. Now the converse part of it we are going to prove. That is, we are going to show that if p is prime, then p minus 1 the whole factorial plus 1 is a multiple of p. Right. Now for that, first we will see what is p minus 1 factorial. P minus 1 factorial is p minus 1 into p minus 2 into etc. into 3 into 2 into 1. And each of the element a belonging to this 1, 2, 3, that is the set 1, 2, 3, etc. p minus 1 has an inverse b in that same set, that is in 1, 2, 3 among p minus 1, such that a into b is congruent to 1 modulo b. Now, if you take, for example, I shall very quickly explain what it is. If you take p to be equal to 5, and in that you consider the numbers 1, 2, 3, and 4. Now, 1, that is within the numbers 1, 2, 3, and 4. 1 into 1. Here, if a is 1, then b is also 1, and it is congruent to 1 modulo b. Now, take the case of 2. If a is equal to 2, then b is equal to what? B should be equal to 3, because 2 into 3, 6 is congruent to 1 modulo b. Now, similarly, if you take the next number a equal to 3, then b should be equal to 2. So here, such existence of numbers are called inverses. That is, b is an inverse of a if a into b is congruent to 1 modulo b. And this inverse, of course, is a unique one for each element. Now, we are going to show that there exists exceptional cases of numbers, that is among the sets within the set 1, 2, 3, etc. P minus 1, such that their inverses are themselves. We are going to show that such two numbers are the number 1 and P minus 1. For that, we are going to see, yes, x into x is congruent to 1 modulo P. That is, x square is congruent to 1 modulo P. It means what? X square minus 1 is congruent to 0 modulo P. We have taken 1 to the left hand side. That in turn again means x plus 1 into x minus 1 is congruent to 0 modulo P. Now, this can be rewritten further as what? X plus 1 is congruent to 0 modulo P. That is one solution, case 1 we are having, which means what? X is congruent to minus 1 modulo P. And what is it? Instead of writing minus 1 modulo P, we can have P on both sides. And the result that we get is X is congruent to P minus 1 modulo P. And for X minus 1 congruent to 0 modulo P, we directly get X is congruent to 1 modulo P. So, in other words, 1 and P are the two numbers whose inverses are themselves. So, in the case that is in the earlier ones, when I described the same with 5, I said the number 1. The number 1, if A is equal to number 1, then B is also equal to the number 1. Similarly, for that is 1 into 1, 1 into 1 is congruent to 1 modulo 5. Similarly, in the case of 4, that is P minus 1 when P is equal to 5. It is 4 into 4, that is 16, and 16 is of course congruent to 1 modulo 5, because 16 minus 1, that is 15, is a multiple of 5. Now, in P minus 1 factorial, congruent to P minus 1 into P minus 2, etc., 3 into 2 into 1. Yes, we are directly writing. We can very well say X is congruent to X modulo P, Y is congruent to Y modulo P. So here also we are saying P minus 1, the whole factorial, is congruent to P minus 1 factorial modulo P. Now the right hand side, that is P minus 1 factorial part, we are going to rewrite and make the final solution. Yes, next page, sir. Yes, how is that done? P minus 1, the whole factorial, is 3 into 3 inverse. Here 3 inverse actually means that particular number with which when multiplied by 3 gives its congruent, such that it is congruent to 1 modulo P. That particular number is 3 inverse, right? Similarly, 4 multiplied with 4 inverse. What is 4 inverse? 4 inverse is that one particular number in the set 1, 2, 3, 4, etc. up to P minus 1, such that 4 into 4 inverse is congruent to 1 modulo P. And finally, we are grouping each number with its inverse and writing the product. Hence, two numbers remain. Which are they? The number 1 and P minus 1, which are inverses of themselves. So 3 into 3 inverse, 4 into 4 inverse, of course, they all result in 1 on the right hand side. And on the left, we have P minus 1, the whole factorial, to be congruent to P minus 1 modulo P. Now, P minus 1 can be replaced by minus 1, as we have seen earlier. And so, P minus 1, the whole factorial, is congruent to minus 1 modulo P, or P minus 1, the whole factorial plus 1 is a multiple of P. And this is possible when P is a prime number. That's it. So, we'll see. Yes. Now, sir, the initial stage. Yeah. Now, these are the conclusive part of my lecture. Here, I will be giving only, sir, a little more to the initial stage, sir. Yes, yes. Again, a little, yes. First one is Lagrange's 4-square theorem. Now, it is also called Bash's conjecture. It states that every natural number can be represented as the sum of 4 integer squares. That is, given any natural number, it can be expressed as the sum of 4 squares. Here we have seen some demo. That is, the number 3 can be explained, can be written as 1 square plus 1 square plus 1 square plus 0 square, and 11 equal to 1 square plus 1 square plus 3 square plus 0 square. The number 28 as 1 square plus 1 square plus 1 square plus 5 square. And this representation is unique. In fact, it is these theorems are not for the elementary number theory part. It is based on algebraic number theory. That is, it forms the basis or higher theorems of algebraic number theory. But yet, I included this as a part of conclusion in my speech. Now, the next one, something much more interesting, Fermat's two-square theorem. Now, two-square theorem is applicable for all those prime numbers which are of the form 4k plus 1. Now, what does that state? Yes, the statement goes this way. Two-square theorem states that every prime number of the form 4k plus 1 can be expressed as the sum of two squares. Yes, ready example 5. 5 is a prime number and it is of the form 4 into 1 plus 1. So 5 we can express as a sum of the squares, that is 1 square plus 2 square. And 13, of course 13 is a prime number, it is of the form 4 into 3 plus 1. So 13 we can write as 2, and we can write 13 as 2 square plus 3 square. 17 is 4 into 4 plus 1. Yes, and one bigger number I have written, that is 241. 241 is 4 into 60 plus 1. Now that we can write as 4 square plus 15 square, and a little more bigger number, that is 277, which we can write as 4 into 69 plus 1, and that is equal to what? 9 square plus 14 square. Right. Now, today, on this occasion, we begin and end with Ramanujan again. So, I selected Ramanujan-Nagel equation to conclude my speech. Now, Ramanujan-Nagel equation, it is given by 2 raised to n minus 7 equal to x square. Yes. Now, what is the specialty of this equation? 2 raised to n minus 7 equal to x square. This equation has solutions in natural numbers, that is positive integers. Excuse me. Only when n is equal to 3, 4, 5, 7 and 15. That is in 2 raised to n minus 7 equal to x square. Whenever n takes the values 3, 4, 5, 7 and 15, we get the corresponding values of x as x equal to 1, 3, 5, 11 and 181. That is, yes. Let us see the first one. 2 raised to 3 minus 7. 2 raised to 3 is 8. 8 minus 7 is 1. And of course, x will be equal to 1. 1 x square equal to 1. So x, on taking the square root, we get it as 1. Next one is, yes, when n is equal to 4, 2 raised to 4 minus 7, that is 16 minus 7, it is equal to 9. And 9 is equal to what? 3 square. So x is equal to 3. And the next one is n equal to 5. That is 2 raised to 5 minus 7. It is 32 minus 7. That is 25. 25 is equal to x square implies x is equal to 5. And further we have 2 raised to 7 minus 7. That is 2 raised to 7 is 128. 128 minus 7. When the difference is taken, it is x square. It means x square equal to 121. Of course, we are taking only the positive roots. X square equal to 121. That means x equal to 11. And the final one, 2 raised to 15 minus 7, it is 32,768 minus 7, that is 32,761, that equal to x square. And of course, the square root when it is taken, the positive square root when it is taken, it is 181. Now, the specialties of this equation, there is a important features of this equation I have stated here. That is, this equation was conjectured in 1913 by our great Shri Ramanujan. That is our great mathematician on whose occasion today we are all speaking. Right? Yes. It was proposed independently in 1943 by the Norwegian mathematician Wilhelm Juguan. Right. I hope I haven't missed the pronunciation. And the final one is, it was proved by the Norwegian mathematician Trygve Nagel. So the name Ramanujan-Nagel equation. And with this, I am concluding my lecture. And once again, I thank Pi Mathematics Association for giving me, and especially that is Shivaraman sir, for calling me and giving me this type of a platform to perform. In fact, I was a slight nervous too. in order to speak because I do not have this type of an experience as stated earlier. And the other ones who are speaking other than me, as I told earlier, are eminent professors. Their preparations are so superb and they were presenting very higher topics. And so I feel that my topic was quite good, engaging, interesting, and that's it. So I thank Pi Mathematics Association once again for giving me this very good opportunity to speak online. And as far as my knowledge is concerned, this is being watched by many people all over the world, including my friends, my colleagues, etc. So thanks. Thank you.
Thank you very much, Shri Rintoo Divakaran sir. So you have taken a lot of efforts to handpick the elementary and fundamental results of number theory. So and provided it in a sequence. So the students follow the sequence and grasp the theorems which you had explained. They would have a solid foundation in number theory. I really thank you for that, especially to mention about the existence of infinity of primes and Fermat's little theorem, among others. So I really thank you, sir. And I remember that when I took engineering classes way back in 2006, there in cryptography class, our professor was talking about Euler's torsion function. So even though these concepts are fundamental in number theory, they have deep applications in science and technology, like in cryptography, among others. So I still remember that. So you have taken the concepts which are both elementary and fundamental, and which also have deep applications in science and technology, sir. We thank you for that. And one more interesting fact, audience, I would like to share about our distinguished speaker. So I came to know that our Rintoo Divakaran sir has also won prizes in the famous puzzle forum, the mathcontest.com. So I'm sure our distinguished speaker has participated in many math puzzle forums across the globe. So we take pleasure in taking his lecture today. Uh, so, so students, now if you have any questions for Rintoo Divakaran sir, I request you to please type it in the comments section so that our sir can answer those questions for you and you can make use of his knowledge. Vijay Kumar sir, any questions from the students so far, sir?
No, Kalyan, not yet.
Okay, okay. Sir, sir, you have any questions, sir?
Not now, sir. You can go for out of things.
Okay, okay. So in that case, so I request Mr. Shankar from our Pi Mathematics Association to deliver vote of thanks to our distinguished speaker.
Good evening, everyone. I would like to thank our speaker, Rintoo Divakaran, for enlightening us with this knowledge and spending quality time with us. I feel today's lecture gave deep insight into number theory and also revealed some interesting facts and theorems. Thank you so much, Professor. I would also like to thank Professor Sivaraman for inviting a couple of senior professors from various reputed university on this wonderful occasion. I want to thank the PMA team who really worked hard to make this 2 days event successful, especially Vijay Kumar, trustee, for setting up the YouTube streaming service. Finally, thanks to all students present here for paying attention and learning. I would like to end my speech here. Thank you.
Thank you, Shankar. So, சொல்லுங்க சார்.
இல்லை நீங்கள் முடிச்சிடுங்க, என்னோடது வேண்டாம் சங்கர்.
So once again, I thank Shri Rintoo Divakaran sir for his lecture and all the students and the participants for attending the lecture today. So we have come to the end of the second day of the PMA Ramanujan lecture series. So we had lectures delivered from 6 eminent experts. I hope the students enjoyed the sessions a lot and they learned a lot. So I'm happy to announce that our Pi Mathematics Association will be very soon uploading all these lectures in the YouTube platform. So I request all the students to make maximal use of these lecture materials to enrich their mathematical knowledge. And I also request them to contribute to Pi Mathematics Association in future. So thank you, everyone. So we are officially ending this session and also the PMA Ramanujan lecture series.
Thank you, Rintoo Divakaran, for providing the lecture.
Thank you, sir.
Thank you.